Hi guys, welcome to Unit 1A, Notes C. Today we're going to talk about some graphical techniques, specifically ways that we're going to use graphs and graphing skills in our labs. So first thing you should know is IB labs pretty much have to always have a graph. IB considers graphing to be a better way of averaging your data because it is two-dimensional. Instead of just a one-dimensional average, which would be your typical average of taking 3 or 4 data results, not data results, 3 or 4 answers, and averaging them together by adding and dividing by the number, your typical, the way that you've averaged since grade school. That's one-dimensional. Graphing actually produces a two-dimensional average where the slope is typically what you're looking for. In order to get the correct graph, in order to get a graph that is actually going to tell us about a trend, we really don't want what's called a line graph on Excel, where it kind of plays connect the dots for you. What you really want is something called a scatter plot. And then you're going to insert a trend line. So a trend line is different than what would show up from an actual line graph. So be sure you're looking for scatter plot. And then after we get that pulled up, then we can tell it to give us a trend line. When we do this, typically the independent variable goes on the x-axis and the dependent variable goes on the y-axis. So you may remember a little acronym trick for this. Dry mix. So the dependent variable is the one that's responding and it goes on the y-axis. And then the manipulated variable is your independent variable and it goes on the x-axis. So this is going to kind of help us keep track of what is responding, where y is a function of the change in x. You want to make sure that your axes labels have the quantity, the unit, and then something new here, uncertainty. We always want to include the uncertainty on our axes labels, and we're also going to account for uncertainty with something new called error bars. We want to make sure that you're really thinking about the uncertainty and using the graph to communicate the effect of the uncertainty on your data. The other thing that you should have, well, I just talked about the error bars. The other thing that you should think about now, something that we didn't really focus on in honors, was whether or not you should set the y-intercept. And that's a setting that's in the same place as where you would insert your trend line or your R-squared value. You can also just tell Excel to set the intercept to 0, 0. Sometimes that makes sense and sometimes it doesn't. It's a decision you have to make for every single lab. Does it make sense that if the x value is 0, would the y value be 0? So an example of where that would make perfect sense is what if I wanted to graph mass and volume in order to determine density, where density would be the slope. Well, if I have 0 mass, then I probably don't take up any space, so an object or nothing with mass would also take up no space. 0, 0 makes sense. Where that wouldn't make sense is a lab where we're trying to determine the boiling point or the plateau and the phase change graph. So in that case, why would I want to set my intercept to 0 and throw off all of my numbers, an arbitrary 0, 0 value that actually isn't true? In that case, we would definitely not want to set our y-intercept to 0, 0. So it's a decision that you have to make based on what type of graph and what the lab really is. So these are all things we want to consider anytime we make a graph. All right. Next, I want to make sure that we're using some correct terminology. When we are making inferences based on a graph, we've done a lot of given the x value, read to the y value, or vice versa, in order to interpret things from a graph. I want to make sure that you're using the correct term based on whether that point of intersection, that point that we're reading to, is between the values or outside of the values. There are actually 2 different terms, even though both of these things really just are taking an inference that the trend applies to the point in question. If you are inside of the data points, so we have actually plotted data, that would be A and B point here. If you're between 2 points, we would call that interpolation, assuming the trend line applies inside or in between the data points. If you are outside, making the inference that the trend applies further or behind, going back towards the y-intercept, that would be extrapolation. assuming the trend line applies outside of the quantities tested. So two different terms to assume the trend line applies based on whether we're between points or outside of the points. Inter or in between, interpolation, or exterior outside, extrapolation. Two different terms. All right, so I mentioned that the slope can really give us a lot of information. That's typically what you're looking for 9 times out of the 10 in our labs. So we want to talk about how to tell what the slope could really mean. So you should be familiar with the idea of what a slope is, typically rise over run or the change in y over the change in x. So let's look at a couple examples and try to figure out what the slope might mean. So let me write the rise over run, or the slope, m, for my first example here. The rise, or the change in y, would be PV over the run, or the change in x, would be NT. So you may recognize these variables from our ideal gas law. So let me go ahead and jot that down here. PV equals nRT. And you might see where I'm going with this now. If I were to try to recreate this, it would involve trying to isolate R by dividing both sides by NT, which of course means they cancel out on this side. And so PV over NT is equal to R just by manipulating the ideal gas law. So that means if I get my slope to be PV over NT, then the slope would actually be R. This would be a way that we could experimentally determine our gas law constant. Let's look at my next example where I'm looking at moles of water and moles of anhydrate. So this is going to be related to our hydrate lab. The hydrate lab from honors involves copper sulfate attached to some number of water molecules. And our goal was to calculate or identify N, or the number of water molecules per copper sulfate. So this is essentially an empirical formula situation. I want basically a mole ratio of how much water compared to how much copper sulfate. Well, let's look at what we get if I do rise over run here. What would the slope represent? My rise, or my change in y, is the moles of water. And my run, or my change in x, is my moles of anhydride, which is essentially what we did in a one-dimensional way in honors, looking at the mole ratio of water to copper sulfate. If I plotted doing this multiple times, the slope could get me my hydration number, or N. So the idea is that you've got to think ahead. You're going to have to determine your dependent and independent variables for yourselves in the labs. And so in order to determine the best X and Y thing to plot, you've got to start thinking about what you want your slope to be. Think about the data you want to collect in order to get that slope, and then reverse engineer what should your independent and dependent variables be. Thinking from what slope you're looking for. All IB labs, honestly, to get a good score, need a graph. And if you're trying to make a graph of a relationship, that slope should probably mean something. So figure out what you're looking for in the slope and then work backwards to your variables. What do we want to change on purpose? And what is going to respond as a function to that? And that's going to help you identify your dependent and independent variables in the labs. All right. So in IB, you also have to be able to calculate the slope by hand. So there's a couple of specific things. Like IB can be very nitpicky and particular about things. There's some specific things that they're looking for if they ask you to calculate the slope by hand. So the first thing that you should know is, assume we've already made our graph in our 1, 2, 3, 4, 5 points trend line. Now we want to calculate the slope of the trend line. So we would want to pick out points on the trend line, not graphing just the slope of 2 data points. So that's not going to give you the trend. That would give you just the relationship between 2 points. We want the slope of the trend. And so you would need to graph out the actual trend line, like use a ruler, make it nice and straight, and then be able to kind of read your graph in order to pull 2 new points from the graph trend line itself. Absolutely do not use the data points themselves, even if one of those data points looks like it falls on the trend line. Because one of the points for the IB exam is knowing better than to use data points. So why would you give them an excuse to mark off? Do not use the data points. Use completely new points that were absolutely not given. New points from the graph, even if it looks like it falls on the trend line. Don't give them an excuse to count off. The other thing I want to do is try to pick points kind of far away from each other. Again, just trying to get a better average from picking points that are different. If we pick points right next to each other, it just wouldn't be as good of an average. So the idea is I'm trying to look for some spacing. I would stick with interpolation, personally, just trying to get points that are as far apart away, but not really outside, completely outside of the data that was given. My advice, just to get the best results. The other thing that you want to do is to make it really clear for the grader what points you chose. So I would circle those points on the graph. The graph itself should contain 5 data points that are actually solid points, like filled in points. Then the trend line drawn with a ruler. Then hollow points or circles on the trend line to show where did you get the points used to calculate the slope. So I want to make sure that we're clear on what we've chosen and that we're choosing the right things. The other thing that you've got to be careful of is using the 0, 0. So we talked about how sometimes it's okay to set the y-intercept to 0 if it actually makes sense that when your x is 0, your y is also 0. Your x is y. The idea, though, is that if you do set it to 0, it still has error. It's not this perfect pure number. It's still a point on a graph. So it's still going to affect the propagation of your uncertainty. The other thing, just kind of from my perspective, is it's not really a data point. You didn't collect it. It's kind of more of an inference. So it always kind of makes me uncomfortable when you see 0, 0 as one of the points. But technically, IB will give you credit if you show your work. Think also about when you're doing the subtraction to find the change in something. It could also be affecting your sign. So there's just a lot of things that you've got to be really careful of if you choose 0, 0. And again, I don't think it's a really good choice because I don't really consider it data. I would just recommend avoiding using the 0, 0. IB will give you credit if you do it right. All right, now let's talk about the R-squared value. So whenever you use Excel to create a graph, you're going to insert your trend line, and then in that same exact point, or same exact menu, you can also tell it to select the R-squared value. You always want to include that on a graph because that's going to describe the strength of the correlation of your data. An R-squared value of 1 would indicate that every single data point is exactly on the line. Kind of, careful of your terminology, but kind of like saying it's a 0% error, that everything is 100% aligned. But you wouldn't really use percent error as the terminology. You would describe it as a strong correlation. The absolute strongest correlation would be an R-squared of 1. Whereas on the flip side, a very low R-squared value, I don't think you can get an R-squared of 0, but say like an R-squared value of 0.3. That's terrible. That's like the data points are all over the place and I'm just guessing at a trend. And there's of course values all in between. Ideally, you want an R-squared value of greater than 0.9 to indicate that it's a strong correlation. And then you can start using qualifiers to kind of knock down the strength. Well, it's relatively strong, maybe if it's at 0.85. Ideally, you want above a 0.9 to indicate kind of a successful lab or well-correlated data. The R-squared is essentially telling you how close together the points are to the line. One thing that I see a lot is really not okay to do is just guessing at the type of trend. Changing in Excel, you can actually change the type of trend line. Most of the time, I'd say almost all the time, we're looking at a linear trend. The only example I can even think of that has like an exponential trend would be like half-life, if you're graphing something with nuclear reactivity, which of course we're not going to do in this class. So typically you're looking for a linear trend so that you can indicate specifically a direct or an inverse relationship, which is only going to be possible with that linear trend to show that it's specifically if x increases, y increases linearly. So don't just change the trend type just because you get a better R-squared value. It's also going to mess up your trendline equation, which half the time you need in order to interpret your data. So don't just change things around just because you want a low R-squared value. Typically the answer is redoing just one individual trial or level of the lab itself. All right, let's talk about error bars. This is the new piece of what we're going to add on to our graph. So error bars are exactly what we have pictured here, where we have kind of a bottom and top range. It's kind of showing the absolute uncertainty or the range of the data. This is my actual measurement, but then it had an uncertainty of plus or minus this much. So the idea here is that the range of values is shown by this extra marking that you see. And so the extra marking typically depends on the uncertainty of the tool. So a small range would indicate a very precise tool, where a large range would indicate a less precise tool. And if you do have uncertainty in the x direction and the y direction, you typically see this crisscross here. There's actually something I want you to be really careful about when you're using Excel too. When you insert error bars, typically we've been very careful to use the most precise equipment that we could. And so typically error bars are tiny. They're very small and they look like almost little crosshairs on every dot. So my advice would be to shrink the dot. You can actually change what they call the marker size and to make the dot smaller so that you can actually see the error bars. Then you can set the error bars to see, or before you, no, I would do change the marker size first because it's easier to click on, and then set your error bars to the exact size that you want them. And in Excel, you can tell it what marker size you want, and it will uniformly apply it to all of them. It won't be different like this, where this one's small and this one's large. But that kind of makes sense because typically you would be using the same tool to measure a specific variable. So you would want uniform error bars. Once you do that, you want to look at how the trend line lines up with those error bars. And this can actually tell you a lot about your sources of error. Ideally, we would like our trend line to be drawn within the error bars. If you cannot get your trend line to fall within the error bars, that would indicate that your systematic errors are large. You have large systematic errors. They are greater, have a greater effect on your lab than your random errors. And this should drive your sources of error discussion. Once you determine that systematic errors play the largest role, you should really focus on systematic errors in your sources of error section. If you did fit the trend line in all of the error bars, then that would indicate that random errors play a more prevalent role, and your sources of error section should focus a lot on random errors. So you kind of want to let that, the evaluation about your trend line versus your error bars kind of drive your source of error discussion. Something that you should evaluate in the evaluation section. All right, last little trick I want to show you is how to linearize something that doesn't seem to be linear. Because as we mentioned, we really want a linear graph with a low R-squared value. That's kind of the goal usually. So not all data automatically produces straight lines, but that's what we want. So how do we fix that? So let's look at a function here, something that's graphing y versus x. And as you can kind of tell by the data, this is not going to be a linear function. It's going to have a very different shape, here we go, of y versus x. It's going to not be linear, and forcing a linear line on it wouldn't make any sense. We'd have a terrible R-squared value. That's not the way that these two variables are related. But how could I make a linear graph out of this data? Well, if I actually did a calculation to find the square root of x and then graphed that, the square root of x, the function of y, well, y as a function of the square root of x, sorry, then that would give me the linear line. And notice the data table now expands to show the data that is going to be graphed. Remember in lab reports, you only show a sample calculation. I would only show one time showing how to get from x to square root of x, but then I would want to include a results table that showed what data was graphed before showing that graph. Just a heads up on the communication that they're looking for there. So going back to this, it seems as if it's not linear. But if you actually look at what is directly proportional, y should be directly proportional of x, of square root of x. And so if I calculate square root of x, then I get my direct proportion. So let's look at one other example here. Now I have y equals ka3 squared, or can't talk today. Y equals k times a cubed. So if I just plotted y as a function of a, well, that's not linear because those aren't directly proportional out of the equation. What is directly proportional is y versus a cubed. So if I plotted y versus a cubed, then poof, I have my linear graph, my direct proportion, where the slope would be k. So that's a nice trick to be able to make data that doesn't seem linear actually become linear. Just be careful in the way that you present that. You want to make sure that you're communicating exactly what you're doing, keep it in chronological order as you go through your report. All right, guys, that's going to do it for Unit 1A, Notes C. Our next unit is Unit 1B, Notes A, and we're going to start going through some more stoichiometric relationships. I'll see you there.